Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into the mysterious and fascinating world of black holes, those invisible giants that bend space and time in ways even Einstein once doubted could exist. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the beginnings of black holes together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine the universe as a vast, dark ocean, and our voyage tonight will take us through currents of history, physics, and imagination, revealing how black holes first entered human thought, why Einstein hesitated to believe in them, and why they continue to challenge the deepest laws of nature. Take a deep breath, let it go, let the stars above you and the science around you lull your mind into a gentle stillness. The story begins not with light, but with the quiet possibility of darkness. Long before Einstein ever wrote down the equations of general relativity, humans were already imagining the possibility of stars so massive and dense that not even light could escape their grasp. In the late 1700s, two thinkers, each working independently, contemplated what we now call dark stars. One was John Michel, an English clergyman with a keen fascination for astronomy. The other was Pierre-Simon Laplace, a French mathematician and philosopher who pondered the same idea through the lens of mathematics. Both asked a question that seems almost fantastical. Could a star be so massive that its gravity would prevent light itself from escaping? To understand this idea, we can picture something familiar. Imagine throwing a ball straight up into the air. On Earth, no matter how hard you throw, the ball eventually comes back down. The force pulling it back is gravity, and the speed it would need to reach to escape Earth completely is called the escape velocity. On Earth, that speed is roughly 11 kilometers per second, which is astonishingly fast, much faster than any human can achieve without a rocket. For a star like the Sun, the escape velocity at its surface is even greater, around 400 kilometers per second. Now, Michel and Laplace asked, what if a star were not only massive but incredibly dense? Could it be so powerful that the escape velocity would surpass the speed of light itself? If so, any light emitted from such a star would be trapped forever, making the star invisible to the eye. Laplace described this idea beautifully, suggesting that the largest objects in the universe might go unseen because of their magnitude. Michel and Laplace's dark stars were theoretical constructs, imagined in a time when Newtonian physics ruled, and the concept of light as a particle obeying classical laws seemed sufficient to explore the cosmos. They missed an important piece of the puzzle, one that would not be discovered until centuries later. You could increase the escape velocity not only by adding mass, but by compressing matter into a very small space. A modern analogy illustrates this clearly. If the entire Earth were compressed into a sphere less than a centimetre across, its surface gravity would become so extreme that light could not escape. In that tiny, unimaginably dense form, Earth itself would become a black hole, a concept Michel and Laplace could only imagine in part. These early musings laid the groundwork for a subtle but profound shift in our understanding of gravity and space. They were the first hints that nature could harbour objects so extreme that our everyday intuitions about light, matter and motion would no longer apply. The dark stars were more than a curiosity. They were a precursor to a universe where boundaries could be invisible and where the very fabric of reality could bend under the weight of mass. As we sit quietly and imagine these early thinkers staring at the stars, calculating, imagining, and dreaming of invisible giants, it's worth noticing something gentle and almost poetic. The human mind, even centuries ago, was reaching toward the extremes of possibility. Michel and Laplace didn't need telescopes to see the invisible. They needed imagination, careful reasoning, and the courage to consider that the universe might be stranger than it appeared. Their work reminds us that every profound scientific discovery begins with a question that seems impossible or fantastical. So, as we drift further into the story, we carry with us the sense of quiet wonder that those early astronomers felt. From dark stars in a Newtonian universe, we will soon journey toward Einstein's radical reimagining of gravity, a theory that made the concept of black holes not just possible but inevitable. And in that shift, from imagination to mathematical certainty, we will see why even the greatest mind of the 20th century paused and questioned. Could such objects truly exist in nature? For now, let your mind rest with the image of these hidden stars, their light forever trapped, and the gentle tug of gravity shaping the silent depths of the cosmos. As we leave behind the imaginative dark stars of Michel and Laplace, let us step forward into the world of gravity as it would be reimagined a century later. Newtonian physics, with its elegant simplicity, allowed us to predict the motions of planets, the fall of an apple, and the paths of comets with remarkable accuracy. It taught us that gravity is a force, an invisible tug between objects with mass. The larger the mass, the stronger the pull. The closer the distance, the greater the effect. It was a universe that felt predictable, orderly, and safe in its consistency. But as our understanding deepened, and as we began to consider the extreme conditions of space, something in Newton's model began to feel incomplete. Imagine, if you will, the gentle fabric of space stretching outward, like a finely woven sheet suspended across the vast cosmos. Place a heavy object, such as the sun, upon it. In Newton's picture, the sun tugs at the planets, pulling them along invisible strings. The planets respond faithfully, tracing their elliptical paths around the sun. But in this fabric analogy, we can begin to imagine an alternative. Perhaps the sun does not pull at the planets at all. Perhaps the planets follow the curves of the fabric itself, tracing the straightest path through a space that has been subtly bent and stretched by the sun's mass. This was the vision that Einstein brought to life in 1915 when he introduced the theory of general relativity. Einstein proposed that gravity is not merely a force, but a property of geometry itself. Mass and energy warp the fabric of space and time, and objects move along these curves naturally, without any need for invisible strings or tugs. A planet orbiting a star is not being pulled in a conventional sense. It is simply following the curves in the space-time landscape created by the star's presence. Time, too, is affected. It can slow down in the presence of intense gravity, like a river flowing more sluggishly through a deep valley. In this universe, space and time are intimately connected, bending together in response to the distribution of mass. It was within this framework that black holes could finally be understood with new clarity. Einstein's equations showed that under certain conditions, the curvature of space-time could become so extreme that all paths lead inward, toward a point from which nothing, not even light, could escape. This was a radical leap from Newton's world of forces and balls rolling along invisible slopes. Suddenly, the dark stars of old became more than speculation. They could exist as precise solutions to the equations of general relativity. And yet, even in this revolutionary picture, Einstein himself was hesitant to accept the physical reality of such objects. To him, singularities, points where density becomes infinite and space-time curvature diverges, seemed almost like a mathematical fiction rather than something nature could truly create. Karl Schwarzschild, a German physicist, was the first to provide an exact solution to Einstein's equations for a spherical mass. His work described the geometry of space and time surrounding a non-rotating, perfectly symmetrical star. This solution revealed the concept of what we now call the event horizon, a boundary beyond which the curvature of space-time becomes so steep that all paths point inward. Schwarzschild's mathematics did not demand that such objects exist in nature. It only showed that if a star was sufficiently compact, the equations permitted a region where escape is impossible. Here, the universe bends so sharply that an imaginary marble rolling along the fabric would inevitably spiral inward, never to return. This is where Einstein's caution becomes understandable. The equations could describe an extreme, almost surreal possibility, but could the universe actually produce such conditions? For decades, many physicists thought not. The idea of a star collapsing into a singularity was both fascinating and unsettling. Imagine a star once shining brightly, compressing its entire mass into a point smaller than a city, while simultaneously bending the surrounding space-time into a funnel so deep that light itself cannot escape. It is a vision both awe-inspiring and difficult to accept. Even the numbers themselves are staggering. For a star like our Sun to become a black hole, it would need to be compressed into a sphere only about 6 kilometers across. To imagine it is to shrink an object that dominates the sky to something smaller than a small town, yet containing all its mass, all its history, all its light, and all its matter. Gravity at such a surface would be immense, and space-time around it would warp in ways that our ordinary experience can hardly encompass. Yet, as strange as it seems, the equations are consistent and the physics is clear. Once a certain density is surpassed, collapse is inevitable. Einstein's general relativity, therefore, opened a new door in our understanding. The simple Newtonian picture of gravity as a force is replaced with a dynamic universe, where mass and energy shape the very geometry through which everything moves. Dark stars are no longer mere speculation. Black holes emerge as a natural consequence of extreme mass and curvature. And yet we are reminded that mathematics and nature do not always move in lockstep. Even as the equations permit black holes, nature may still choose not to form them, or so thought Einstein and his contemporaries. As you drift gently through these ideas, imagine the quiet elegance of space-time itself, bending and folding like a soft invisible cloth, carrying planets, stars, and light along its curves. The dark stars of the 18th century whisper into the equations of Schwarzschild and Einstein, leading to a universe where gravity is geometry, space and time dance together, and the seeds of black holes are planted in theory long before their confirmation in observation. It is a place both simple and bewildering, one that invites curiosity, reflection, and a gentle sense of wonder. When Albert Einstein published his theory of general relativity in late 1915, the world of physics changed overnight. Space and time were no longer separate, rigid backdrops to the events of the universe. They had become a single, flexible fabric, what Einstein called space-time, that could bend, stretch, and twist under the influence of mass and energy. It was an elegant vision of the cosmos, one where gravity was not a force reaching out across space, but rather the shape of space itself. Yet within weeks of Einstein unveiling this new theory, another mind quietly found something hidden inside his equations, something Einstein himself did not expect. That person was Karl Schwarzschild, a German physicist and astronomer working at the front lines of World War I. In 1916, while serving in the trenches, he read Einstein's newly published papers and decided to test them. Could one find an exact description of how space-time curves around a single, perfectly spherical mass, like a star or a planet? Despite the chaos of war, Schwarzschild derived what would become the first exact solution to Einstein's field equations. His result described a mathematical object unlike anything physicists had ever seen. It was simple, precise, and, although he did not realize it at the time, something we would later call a black hole. Schwarzschild's equations painted a picture of space-time shaped into a deep, smooth funnel. The closer one moves toward the center of that funnel, the steeper it becomes. Imagine placing a heavy marble in the center of a soft rubber sheet. A small marble rolling nearby would circle the heavier one again and again, tracing a graceful orbit around it. Now imagine adding more mass. The depression grows deeper, the slope sharper, until eventually the sides of the funnel become so steep that any marble rolling too close can never escape. That boundary, the invisible surface where escape becomes impossible, is what we now call the event horizon. In Schwarzschild's model, this horizon forms at a particular distance from the center of the mass, a critical radius determined by the object's size and weight. For the Sun, that distance would be about 3 kilometers. For Earth, it would be less than 1 centimeter. Those numbers sound small, but they represent something vast in meaning. They show that if you compress a massive body tightly enough, light itself can no longer climb out. It's not that light slows down, it still moves at its cosmic top speed, but the space-time around it bends so sharply that all paths curve inward. To an outside observer, anything that crosses that invisible boundary simply vanishes. Schwarzschild's work astonished Einstein. He admired the beauty of the mathematics, but doubted that nature would ever allow such an object to exist. Infinite densities and lightless horizons felt too extreme, too abstract. Einstein preferred the universe to be orderly and comprehensible. He once said that while equations might predict such curiosities, nature would find another way. For the next 2 decades, many scientists agreed with him. They viewed Schwarzschild's solution not as a real description of stars, but as an elegant mathematical curiosity, something to be admired, but not believed. Still, Schwarzschild's discovery had opened a quiet door in the back of physics, one that would never again fully close. The shape of his solution was too simple, too perfect to ignore. It implied that the collapse of a sufficiently massive star could, in theory, create an object from which no light or matter could return. A black star, a dark sphere carved out of the geometry of space itself. Schwarzschild died only a few months after publishing his work, unaware that he had uncovered one of the most important ideas in modern science. His name, though, would forever be attached to that invisible surface, the Schwarzschild radius, the mathematical threshold of no return. For decades, this strange radius remained a theoretical ghost. Scientists debated whether it had any meaning beyond the page. Some argued that it was merely a coordinate artifact, a quirk of how the equations were written. Others noticed something unsettling. From the point of view of an outside observer, time near that surface seemed to slow to a crawl. An object falling toward the horizon would appear to move slower and slower, never quite reaching it, fading into a motionless shadow frozen in time. For those early physicists, this made the entire concept feel paradoxical. How could a star ever finish collapsing if, from our perspective, it never quite completes the journey? The answer, as we now know, lies in the nature of relativity itself. Time can stretch and warp differently for different observers. To a distant viewer, it may appear as though the falling star halts at the brink, but to the star, and to anything crossing the horizon, time flows normally. There is no sudden stop, no invisible wall, only the smooth continuation of space and time into the depths of the funnel. For the traveller, the crossing is uneventful. It is only from afar that the universe seems to hesitate. This subtle dance of perception would take decades to fully understand. But the seeds were already there in Schwarzschild's paper. A simple, symmetrical model of space and time shaped by gravity into something both beautiful and terrifying. It was a reminder that mathematics could reveal truths long before intuition caught up. Inside those equations was a hint of how strange the universe could be when pushed to its limits. And quietly, behind all the skepticism, a few physicists began to wonder whether nature might indeed craft such extremes. When we picture Schwarzschild at his desk, scribbling in the dim light of a wartime evening, it's easy to imagine him unaware of the legacy his equations would leave. His work began as a question about how stars bend light, and ended with the realization that the universe might contain places where light is forever trapped. The horizon he discovered is not a surface you can touch, but a boundary in the flow of space and time itself, a line drawn not in matter, but in the geometry of reality. As you rest with that image, the idea of light caught in a curve too deep to climb, remember that this was the first glimpse of something far larger. Schwarzschild gave physics a key. It would take Einstein, and those who followed, decades to decide whether the door it unlocked led to truth or to an impossible dream. By the 1930s, Einstein's theory of general relativity had already reshaped how scientists thought about gravity. It described the universe not as a vast emptiness filled with invisible forces, but as a living geometry, curving, breathing, responding to the presence of matter. Still, even after 2 decades, Einstein himself remained uneasy about some of the extreme possibilities hidden within his own equations. The most troubling of these were the singularities and horizons that Karl Schwarzschild had uncovered. Einstein accepted the mathematics, but he doubted that the natural world would ever allow such infinities to form. To him, a singularity was a sign that the theory had reached the edge of its usefulness, not a doorway into reality. It was during this period of reflection that Einstein and one of his assistants, Nathan Rosen, began exploring what the inside of those equations might mean if space could somehow be folded in unusual ways. They wondered, if space and time could curve, could they also connect? Could there be tunnels linking two distant regions of the cosmos? In 1935, they proposed a mathematical model known as the Einstein-Rosen bridge. Today, we often call it a wormhole. In their vision, the Schwarzschild solution could be interpreted not as a single pit, but as 2 funnels joined at the narrowest point, forming a bridge between separate universes or perhaps distant parts of the same one. It was an elegant idea, an attempt to remove the uncomfortable notion of a singularity by replacing it with a smooth geometric connection. The bridge allowed Einstein to keep his beloved spacetime continuous, without the tearing that an infinite density implied. But there was a catch. According to the equations, the bridge would collapse too quickly for anything, not even light, to cross from one side to the other. It was as though nature permitted the idea of a tunnel, but refused to let travellers pass through. To Einstein, this reinforced his belief that the universe would never produce a true black hole. The mathematics could suggest such objects, but nature, he thought, would prevent them from ever becoming real. In these years, Einstein's skepticism reflected the mood of much of the scientific community. Most physicists were focused on the emerging world of quantum mechanics, the strange and counterintuitive rules that governed atoms and light. Compared to the new excitement of the quantum realm, general relativity seemed distant, almost philosophical. Few were interested in stars collapsing into darkness or space curving back upon itself. Those who were intrigued often treated such solutions as curiosities, beautiful, yes, but abstract, with no clear connection to the stars we actually see. And yet, there were subtle signs that nature might be more daring than anyone imagined. Astronomers were beginning to observe stars that seemed to defy ordinary expectations. Some were extraordinarily dense, white dwarfs, small as Earth, yet heavier than the Sun. Others, like the newly discovered neutron stars, packed the mass of millions of Earths into a sphere barely 20 kilometers wide. The universe was hinting that matter could indeed collapse into astonishing states. The line between what was possible in theory and what might exist in the night sky was starting to blur. Einstein, ever the cautious thinker, continued to argue that complete collapse, the kind that would create a Schwarzschild horizon, could never happen in reality. He believed that the internal pressure of matter, or some yet unknown physical law, would resist gravity's final pull. He even published a paper in 1939 suggesting that a collection of many small stars could never contract into a single infinite point. He called it a stationary system. It was his way of defending the universe from absurdities. But only a few months later, another team would prove him wrong. Before that turning point, though, the idea of the Einstein-Rosen bridge captured imaginations because it sounded almost poetic. The notion that two distant corners of the cosmos might be connected by an invisible thread felt more like mythology than physics. Some writers compared it to a cosmic mirror, a gateway through which light could fall and emerge somewhere else. The concept has lingered ever since, inspiring stories of interstellar travel and parallel worlds. In truth, the original bridge was fragile and impassable, but the seed of the idea, the geometry of connection, remained deeply human. It spoke to our longing to find pathways through the impossible. Mathematically, the bridge removed the singularity, but physically it didn't solve the deeper mystery of what would happen to a collapsing star. If a massive star exhausted its fuel and gravity gained the upper hand, would it stop at a dense neutron star stage, or would it continue inward, crushing itself beyond recognition? In the quiet offices of Princeton and Berlin, physicists pondered these questions, turning over equations that seemed to describe a place where the rules of time and space themselves could invert. It was a kind of intellectual vertigo, a realization that the same laws that explain falling apples and orbiting planets might also predict the disappearance of entire suns. For Einstein, these extremes clashed with his sense of a rational universe. He was convinced that nature would not allow infinities or horizons that trap light forever. To him, such predictions were warnings that the mathematics had overstepped its bounds, and yet there was beauty in the way those same equations hinted at hidden structure, bridges, folds, and tunnels connecting the unreachable. The tension between belief and mathematics created a subtle melody that still plays in physics today, when our intuition says no, but the numbers whisper perhaps. If you picture the Einstein-Rosen bridge, try to imagine not a tunnel of stone or metal, but a smooth curve in space itself, folded like a ribbon of silk. It shimmers quietly, invisible, connecting two distant points that could never otherwise meet. Time moves differently along its surface, stretching and slowing until the bridge narrows to nothing. You cannot see it, and yet it exists within the logic of relativity, a dream of continuity in a universe that sometimes seems to break apart. As evening thoughts begin to settle, we can sense the strange comfort in Einstein's doubt. His reluctance was not stubbornness, but humility before the complexity of nature. He had rewritten the laws of the cosmos, yet he was unwilling to assume he had reached their end. The bridges he imagined, fragile as they were, became metaphors for curiosity itself, connections between what we know and what still lies beyond reach. And so, as the century crept toward war and discovery alike, a quiet question remained suspended in the equations. If nature truly allows space to fold and time to stretch, could a star one day cross the boundary Einstein hoped would never exist? The universe, as it turned out, was already preparing its answer. By the late 1930s, the conversation about black holes, though still not called that, was shifting from the realm of abstract mathematics to the real stars that glittered across the night sky. Astronomers had begun to observe evidence that some stars lived far more violent lives than anyone had imagined. The universe, once thought to be serene and eternal, revealed itself to be restless. Stars were born. They burned brightly for millions or billions of years, and then, inevitably, they died. It was in their deaths that the cosmos showed its most dramatic face. To understand what Oppenheimer and Snyder accomplished, we must first step quietly into the heart of a dying star. A star lives by balancing two forces, gravity pulling inward and the pressure of nuclear fusion pushing outward. In its core, hydrogen atoms fuse into helium, releasing light and heat that push against gravity's endless pull. As long as there is fuel to burn, this balance holds steady, like a candle that keeps its shape as long as it has wax. But eventually the fuel runs out. When fusion stops, gravity wins. There is no longer a counterforce to keep the star inflated. The great structure begins to collapse. For small stars like our Sun, this collapse ends gently. The outer layers drift away, forming a glowing cloud called a planetary nebula, leaving behind a dense ember known as a white dwarf. For heavier stars, the story is far more dramatic. The collapse becomes unstoppable. The outer layers crash inward and rebound in a brilliant explosion, a supernova. What remains at the core can be even stranger. A neutron star, a sphere barely 20 kilometers wide but containing more mass than the entire Sun. Its atoms are crushed until electrons and protons merge into neutrons, forming matter so dense that a single teaspoon would weigh billions of tons. This was already astonishing, but Oppenheimer and his student Hartland Snyder dared to ask a deeper question. What if a star is even more massive than that? What happens when even neutron matter cannot resist gravity's pull? In 1939, just as the world outside was sliding into war, the two physicists published a paper that quietly changed everything. They used Einstein's equations to describe, step by step, what would happen to a massive star as it collapses under its own gravity. The result was both precise and unsettling. Their calculations showed that nothing in the known laws of physics could stop the collapse. Once a star reached a certain critical mass, its contraction would continue indefinitely, the outer layers falling inward, the density rising beyond any limit. In simple words, the star would keep shrinking, faster and faster, until all of its matter disappeared behind a boundary from which no signal could escape. From the outside, the star would seem to freeze and fade away, its light stretching to red, then to black. But from within, the collapse would go on, unending, toward what general relativity described as a singularity, a point where the known laws of nature simply break down. This was the first true description of what we now call gravitational collapse, the process that forms a black hole. Oppenheimer and Snyder's work was elegant, built entirely on the foundation Einstein had laid. They made no exotic assumptions, no untested physics, only the geometry of space-time and the known behaviour of gravity. The conclusion was unavoidable. If a star is heavy enough, gravity always wins. Nature does not stop at some comfortable limit. It follows its own rules to their end. Einstein, upon reading the paper, was unconvinced. He believed that some unknown mechanism would prevent the collapse, perhaps the internal forces of matter or the dynamics of energy fields. To him, infinite density felt like a failure of theory, not a feature of the universe. Many of his peers agreed. Even Robert Oppenheimer himself would later turn his attention away from this topic, focusing instead on the wartime work that would define his name. For decades, their discovery sat in quiet obscurity, a kind of forgotten prophecy about the hidden heart of gravity. And yet, the universe had already begun to prove them right. In the decades that followed, astronomers would find objects that behaved exactly as the Oppenheimer-Snyder model predicted. Stars orbiting invisible partners, systems radiating intense X-rays from compact regions, and later, the astonishing gravitational signals of merging black holes. All would point back to that 1939 calculation, drawn on paper before such evidence even existed. When we reflect on their work today, it feels less like a discovery and more like a revelation, a whisper from the equations themselves about what gravity truly wants to do when given enough time and mass. Gravity is patient. It does not rush. It folds, draws in and compresses, gently but inevitably. It is the sculptor of the universe, and sometimes its chisel carves too deeply, leaving behind not a shape, but a shadow, a place where space and time themselves seem to disappear. To imagine this collapse is to imagine a rhythm that slows endlessly. From the outside, as the star contracts, time near its surface appears to stretch. Light escaping from its edge is delayed more and more until, at last, it cannot escape at all. To an observer watching from afar, the star seems to linger forever at the brink, its final heartbeat stretched across eternity. But to the collapsing star itself, time continues normally. It crosses its own boundary without hesitation, unaware that from the outside it has already vanished. Two perspectives, both true within relativity, yet forever divided by that invisible horizon. This strange duality, the same event seen in two different ways, would become one of the great conceptual puzzles of black holes. It is both poetic and haunting. The outside universe never witnesses the star's final fall, yet the star itself experiences it completely. In that difference lies the beauty and the unease of Einstein's legacy. Reality depends on where you stand, and time itself is not the same for all who watch it pass. As you picture this, let the image settle gently. A once brilliant star collapsing inward, its light fading, its form vanishing. What remains is not destruction, but transformation, a quiet turning of matter into geometry. The star becomes part of the very shape of the cosmos, leaving behind only gravity, only the curve of space and time itself. It's remarkable to think that this entire story, the birth, life, and death of a star, can be written in the language of geometry, without a single symbol of human invention carved in the sky, just the silent mathematics of nature unfolding, as it always has, in the stillness of the universe. And perhaps that is what makes Oppenheimer and Snyder's work so haunting. They showed us that within the calm laws of relativity lies something deeply powerful, the inevitability of collapse, the quiet certainty that even the brightest of stars must someday bow to gravity's embrace. It is not a story of violence, but of surrender. And in that surrender, the universe creates its most mysterious and beautiful objects. There is something both serene and unsettling about the edge of a black hole. It is not a wall, not a surface one could touch or bounce against, but a boundary in the most profound sense, a point of no return in the flow of space and time itself. This boundary is called the event horizon, a phrase that feels almost poetic, as though it marks not just a place in the universe, but the border between the known and the unknowable. To imagine an event horizon, it helps to start with something familiar. Picture a river flowing toward a waterfall. Far upstream, the water drifts calmly, and a small fish could swim freely in any direction. But as it approaches the edge, the current grows stronger. Eventually, there comes a point where the water rushes so swiftly that even the fastest fish, swimming upstream with all its strength, cannot escape the pull. That invisible threshold, the moment where swimming faster no longer helps, is the river's version of an event horizon. Once crossed, all paths lead downward, inevitably, gracefully, into the fall. Around a black hole, space-time behaves much like that river, though the flow is not of water, but of geometry itself. Space and time are drawn inward, their curvature so extreme that every possible path, every direction light could travel, bends toward the center. Even light moving at its universal top speed finds no path that leads away. The event horizon is the boundary where that transition happens. Outside it, light can still escape to the wider cosmos. Inside it, the geometry of reality itself points inward. There is no turning back. For an observer watching from a safe distance, this region behaves in strange and counterintuitive ways. Suppose you could watch a spacecraft fall toward the horizon. As it approaches, its motion appears to slow. The light it emits becomes redder and fainter, stretched by gravity's pull until it fades entirely. To the distant viewer, the spacecraft never quite crosses the horizon. It simply hovers there, frozen in time, fading into darkness. Yet for the traveller aboard, the experience is entirely different. Their clocks tick normally. They feel no sudden jolt or wall. They cross the boundary without fanfare, continuing inward as though nothing extraordinary had happened. Two perspectives, both true, both consistent with Einstein's equations, yet profoundly different in what they reveal. This difference arises because time itself is not absolute. In strong gravity, it slows relative to weaker fields. The deeper you fall into the gravitational well, the slower your time runs compared to someone far away. Near a black hole, this effect becomes overwhelming. The slowing of time is not merely an illusion or a trick of perception. It is woven into the fabric of space-time itself. From the outside, time seems to stop at the horizon, but inside, it flows onward. This duality creates one of the most hauntingly beautiful paradoxes in all of physics, a boundary where time stops for one observer yet continues for another. For a long while, this strange behaviour confused even the greatest minds. Early physicists worried that if time appeared to stop at the horizon, a collapsing star might freeze forever, never completing its fall. Some thought the horizon was an illusion of mathematics, a trick of the coordinate system rather than a physical feature of nature. But as understanding deepened, it became clear that the horizon was real and that its effects could, in principle, be measured. It was not a solid surface, but a geometric boundary, defined entirely by the paths that light could or could not take. You can think of it as the ultimate one-way door. Matter and energy can enter, but nothing can leave. From the outside, it looks as if the door never quite closes, yet from within, the universe beyond the threshold slips out of reach. This is what makes black holes both terrifying and fascinating. They do not destroy the laws of physics, they simply push them to their most extreme expression. The horizon also carries another quiet implication. It is, in a sense, the surface of a shadow. The black hole itself, the singularity, the place of infinite density, remains hidden behind it, forever unseen. All that an external observer can witness is the horizon's boundary, glowing faintly if matter happens to fall nearby, or perfectly black if nothing disturbs it. The black hole does not reveal its secrets. It shows only its outline, like the dark silhouette of a mountain seen against the last light of dusk. Modern physics has taught us that the event horizon has a kind of elegance beyond its mystery. Its size depends only on the black hole's mass, spin, and electric charge. Three simple quantities that summarize everything about it. No matter what formed the black hole, a dying star, a collapsing cloud of gas, or perhaps even a cluster of particles from the earliest universe, its exterior tells the same story. The details of what fell in are erased. Only those three traits remain, as though the universe were simplifying the chaos of matter into a single smooth form. Physicists call this the no-hair theorem. The name is a playful way of saying that black holes have no complicated features, no tangled histories visible from the outside. They are pure, clean geometry, stripped of individuality. It's a strangely comforting thought. In a universe filled with noise and complexity, black holes offer a kind of stillness. They are the most extreme expression of simplicity, places where the equations of nature distill themselves to their essence. To stand, at least in imagination, near the horizon of a black hole is to glimpse that stillness, to see gravity not as a force but as an endless calm drawing everything home. If you were to hover just outside the horizon, you would feel the immense pull of gravity trying to claim you. Every photon of light you emit would struggle upward, losing energy as it climbed. Its wavelength would stretch until it became invisible. You would not fall through in an instant. Rather, from your own point of view, you would hover indefinitely, watching the rest of the universe speed by. Time elsewhere would seem to accelerate. Stars would age and die, galaxies would drift, entire epochs would pass, while you, caught on the edge of gravity's well, would feel almost motionless. It is both a poetic and a humbling image, a moment drawn out until it becomes eternity. And yet, for all its drama, the event horizon is not a place of chaos. It is calm, silent, and perfectly lawful. Every particle, every ray of light follows the curves prescribed by Einstein's geometry. There is no violence at the edge of a black hole, only the steady continuation of nature's patterns into their deepest form. In that quiet at the threshold of the impossible, the universe seems to whisper one of its simplest truths: even the end of light can be graceful. Beyond the event horizon, where space and time are pulled inward with no hope of return, lies the heart of a black hole, the singularity. It is, in many ways, the most mysterious concept in all of physics. To call it a point feels misleading, because it is not a place one could ever reach or stand upon. It is a moment, a condition where our understanding of reality simply dissolves. At the singularity, the familiar language of distance and duration no longer applies. Space folds in upon itself, time ceases to flow in any recognizable way, and the very framework of the universe seems to vanish. In the simplest mathematical picture, the singularity is where the equations of general relativity predict that curvature becomes infinite, that gravity's strength, density, and the bending of space-time all grow without limit. But infinity, in physics, is usually a sign that something has gone wrong. It is a flag marking the edge of a map, where the known rules can no longer guide us. Einstein himself viewed it this way. He believed that nature would never permit infinities. They were, in his mind, signals that the theory, beautiful as it was, had reached its limits. Yet, for all his caution, the mathematics would not go away. The more carefully physicists studied the equations, the more inevitable the singularity seemed to become. To visualize what happens near a singularity, we have to step outside our ordinary notions of up and down, near and far. Imagine again the river from before, but now as it falls past the waterfall, the water doesn't just plunge downward. The riverbed itself is bending inward, and the flow becomes so steep that every path leads deeper into itself. Space doesn't just direct you toward the center, it is the direction. The flow of time, too, begins to twist. What once was a journey through space becomes, in a sense, a journey through time itself. Inside a black hole, moving forward in time means moving inward, toward the singularity. You could fire your engine, struggle against it, or stretch your hand toward the stars, but everything, including your own sense of the future, is drawn toward that end. In the language of relativity, the singularity is not a point hidden in space. It is the final moment in time. This is perhaps one of the most subtle and humbling ideas ever discovered. When we imagine the universe ending at a point, we tend to picture something like a dot, a speck, a pinhole in the fabric of space. But according to general relativity, what collapses into a black hole does not disappear into a dot in space. It reaches the end of its own timeline. For the matter falling in, the singularity is not a location. It is a moment that must be reached, as surely as tomorrow must follow today. The tragedy, if one can call it that, is that this tomorrow lies forever beyond the reach of the outside universe. Even in this darkness, though, there is order. The equations of relativity continue to describe the approach to the singularity with precision. They show that tidal forces, the differences in gravity between one point and another, grow unimaginably strong. Near a stellar mass black hole, these forces would stretch any object into a long, thin filament, a process often nicknamed spaghettification. The term sounds humorous, but it describes a real physical effect. Gravity's pull on your feet would be vastly stronger than its pull on your head, stretching you out atom by atom. Yet this too happens quietly. There is no explosion, no flame, No impact, only the steady deepening of gravity's embrace, until even the concept of shape loses meaning. Inside supermassive black holes, those millions or billions of times the mass of the Sun, this process would be gentler. The curvature near their event horizons is so large in scale that a person could, at least in theory, cross the boundary without feeling anything unusual. The stretching grows only gradually as one moves inward. For a time, the traveller might see the blackness of the horizon receding behind, while ahead there is nothing, no stars, no light, only a smooth descent into the unknown. It is easy to imagine such a journey as frightening, but in truth it may feel tranquil. There would be no sound, no heat, no visible motion, just the fading hum of the universe outside as time itself begins to slow. And then, as every path turns inward, the geometry of the universe folds too tightly to describe. The curvature becomes so sharp that the concept of before and after ceases to have meaning. Here, the language of physics falters. Relativity alone cannot tell us what happens next. To understand the singularity fully, we would need to unite Einstein's smooth, continuous space-time with the jittering, uncertain world of quantum mechanics. The two great pillars of modern physics, one describing the vast and the slow, the other the tiny and the quick, both work perfectly in their own domains, yet near the singularity, they speak different languages. One sees the universe as a seamless fabric, the other as a restless sea of fluctuations. Where those two descriptions collide, a new theory must emerge, a quantum theory of gravity, something that would bridge the divide between the cosmic and the microscopic. This is why physicists often describe the singularity as the edge of our knowledge, the point where science ends not because there is nothing more to know, but because the tools we have built no longer suffice. It is like standing on a coastline at night, listening to the ocean without being able to see beyond. The waves come and go, each one a hint of something larger and deeper, but the darkness hides the rest. The singularity is that hidden ocean, real, powerful, but beyond our sight for now. Some thinkers have speculated that the singularity might not be an end at all, but a doorway. In certain mathematical models, the geometry of space-time could continue beyond it, connecting to another universe or another region of this one. These ideas, while fascinating, remain untested. To us, confined to the outside world, the singularity is a mystery wrapped in silence. All we can observe are the effects it has on the world beyond the horizon. The orbits of stars, the pull of gravity, the faint whispers of radiation. What lies within remains, for now, an unanswered question. As your thoughts settle with the rhythm of this story, you might imagine the singularity not as a place of chaos, but as a point of stillness, a moment where every motion ends, every vibration quiets, and the universe itself seems to hold its breath. It is the ultimate centre of gravity, the heart of silence. Einstein never accepted that such a thing could truly exist, and perhaps, in a sense, he was right to doubt. The singularity may be nature's way of telling us that there is more to learn, more to discover, a deeper harmony yet to be heard. And as we wait for that understanding to come, through the whispers of new theories, new mathematics, new glimpses of light from the edges of darkness, the singularity remains what it has always been, the quiet end of time and perhaps the beginning of something we have not yet imagined. Time in Einstein's universe is not the steady ticking of a clock that we once believed it to be. It stretches, bends and slows in the presence of gravity. Near a black hole, this gentle warping becomes something almost surreal. Space and time, woven together into the fabric of reality, twist so deeply around the black hole's gravity that our familiar sense of motion and duration begins to lose its meaning. The result is a place where perception itself becomes part of the story. Imagine floating in the calm of space, watching a friend drift slowly toward the dark center of a black hole. At first, everything seems ordinary. Your friend's flashlight shines steadily, their movements clear. But as they draw closer to the event horizon, something strange begins to happen. Their light turns redder, fading into darker shades as though it were struggling to climb out of an invisible valley. The rhythm of their gestures slows, like a film played at half speed. A few moments later it slows again and again, until at last your friend seems to freeze completely at the edge. Their light winks out. From your vantage point it appears as though time has stopped for them. They never cross the horizon. They are suspended there, an image caught in amber, forever hovering at the brink. But from your friend's point of view, the story unfolds very differently. Their clock ticks normally. Their heart still beats. They feel no barrier or boundary, no sense of freezing or delay. The horizon passes beneath them quietly. The stars above grow faint, their light bending inward as they continue the fall. Time continues its steady rhythm, one second following another, unbroken, until the singularity lies ahead. This difference, this profound split in perspective, lies at the core of Einstein's vision of the universe. Both observers are right, yet neither sees the whole truth. Time is not absolute. It depends on where you are and how gravity holds you. It is difficult for the human mind to imagine such relativity, because our everyday experience teaches us that time moves uniformly, everywhere and for everyone. A minute feels like a minute whether you're standing on a mountain or sitting by the sea. Yet even here on Earth, Einstein's laws apply, just too subtly for us to notice. In stronger gravity, say, closer to a massive planet or deeper in a gravitational well, time runs ever so slightly slower. Atomic clocks placed at different altitudes on Earth actually tick at slightly different rates. The difference is so small that it takes extraordinarily sensitive instruments to detect, but it is real. Near a black hole, this same effect grows immense, stretching seconds into years and years into eternity for those watching from afar. To make sense of this, it helps to imagine time as something fluid rather than fixed, in the same way that a stream can flow more quickly or slowly depending on the shape of its bed. Time's flow depends on the curvature of space. Where gravity is strong, the river of time deepens and slows. Where gravity is weak, it races freely. A black hole is the deepest valley in that river, a place where time's current nearly stops for an outside observer, and yet, for anyone within that valley, the flow feels normal. They are part of the river, moving with it, unaware of how slow it appears from the shallows above. This relativity of time is not just a mathematical curiosity. It is a reminder of how intimately our perception is tied to where and when we are. Reality itself is not a single, universal stage on which events unfold in the same order for everyone. It is a tapestry of countless overlapping viewpoints, each stitched together by gravity and motion. Einstein often said that time and space are woven into one fabric, tier 1, and the other deforms. Nowhere is that truer than near a black hole, where even light, the fastest traveller in existence, must bend and slow to follow the curvature of the cosmos. If we could somehow stand safely near the event horizon and look outward, the view of the universe would be astonishing. Time beyond the horizon would appear to race ahead. Stars would seem to move and age quickly. Galaxies would drift, their light speeding up, as though the cosmos outside were fast forwarding through its history. What we see as billions of years might pass in what feels like a few heartbeats. It is as though the entire universe were breathing more quickly, while you are caught in slow motion, watching eternity unfold in real time. It is a vision both beautiful and deeply humbling. The awareness that time itself is relative, that even the notion of now depends on where you stand in the web of gravity. The strange behaviour of time near black holes is also the source of some of their most haunting paradoxes. From the outside, the collapse of a star seems to take forever, its light fading but never gone. From the inside, the collapse completes in moments, one object, two realities coexisting. The idea that both can be true at once challenges our most basic intuitions. Yet this is the quiet power of relativity. It replaces absolute truth with relational truth. What you see and what I see can differ profoundly, and both can still be correct. It's worth pausing to think about what that means beyond the realm of physics. The universe, it seems, is built not from rigid certainties but from relationships, between objects, between observers, between gravity and light, between what we know and what we can never quite grasp. Time near a black hole becomes a metaphor for perception itself. Each of us moves through our own flow of moments, shaped by our surroundings, our histories, our gravity. There is no single universal now, no master clock that unites all experience. There is only perspective. Einstein once described time as a stubborn illusion, but a persistent one. Near a black hole, that illusion frays, revealing a deeper structure, a cosmic relativity that allows both stillness and motion to coexist. To stand on the edge of that revelation, even in imagination, is to glimpse the quiet flexibility of reality itself. As you rest with this image, think of the river again, flowing through valleys and plains, over rocks and roots, winding toward some distant sea. Each droplet moves according to the same laws, yet each follows its own path. Near the waterfall, the current slows and deepens. Far away, it rushes freely under the sunlight. Neither view is wrong, they're simply parts of the same whole. So too is our experience of time, stretching and bending under the weight of gravity, yet always, in its own rhythm, carrying us forward. And perhaps that is the lesson hidden in these cosmic distortions, that the universe is not divided between fast and slow, light and dark, inside and out. It is one great continuum viewed from many shores. Near a black hole, we see that truth most clearly, the stillness that looks eternal from one side and the unstoppable flow of time from the other. Both are real. Both are the universe, quietly showing us that perception, like time, depends entirely on where you stand. By the middle of the 20th century, the idea of black holes had drifted, half forgotten at the edges of physics. Einstein was gone. Oppenheimer's 1939 paper lay buried beneath the urgency of wartime science, and most physicists had turned their attention to smaller mysteries, the strange behaviour of atoms, the probabilities and uncertainties of quantum mechanics. The cosmos, for a while, grew quiet in their imagination. Yet in that quiet, a few minds began to listen again to gravity's deeper whispers. One of them was a young English mathematician named Roger Penrose. In the 1960s, Penrose looked again at Einstein's equations and asked a question few dared to revisit. If gravity truly pulls matter without limit, what happens when the collapse begins? Is there any escape, any hidden geometry that could prevent the singularity Einstein feared? His approach was unlike the physicists before him. He thought not in numbers or approximations, but in geometry itself, pure shapes, lines, and structures within space-time. Using this geometric lens, Penrose proved something astonishing. Under almost any realistic condition, if a massive star collapses beyond a certain point, a singularity must form. Gravity, when left to its own devices, does not pause or stabilize, it completes its work. This result was profound because it removed the last traces of human hesitation from Einstein's equations. The singularity was not an artifact of a perfectly symmetrical model or a mathematical trick. It was the inevitable end of gravitational collapse. And with that realization, the universe became more mysterious than ever. Penrose had shown that the singularity was not a flaw in the equations, but an unavoidable feature of space-time itself. The door Einstein had kept half closed swung open once more. Around this time, another mind was quietly waiting on the threshold of discovery, a young physicist at Cambridge named Stephen Hawking. Hawking was captivated by Penrose's theorems, but also driven by a question of his own. Could these same rules apply not just to the death of stars, but to the birth of the universe? If gravitational collapse created singularities, could cosmic expansion begin with one? He and Penrose began to collaborate, blending mathematical precision with philosophical wonder. Together they reimagined the singularity not as a boundary to be feared, but as a clue, a signpost toward a deeper theory of reality. Their combined work was a kind of dance between two disciplines. Penrose brought the elegant visual logic of geometry. Hawking brought the restless energy of theoretical physics and quantum thought. The result was a revolution. They showed that singularities were not rare exceptions but natural outcomes of Einstein's laws. Wherever matter became dense enough, space-time itself would curve so tightly that the normal rules of distance and duration would fail. Singularities, in other words, were woven into the universe's design, appearing at both ends of time, in collapsing stars and in the very beginning of creation. It was a strange realization that the same mathematics describing a dying star could also describe the birth of everything. The universe, it seemed, had symmetry in its mysteries. But Hawking was not content to stop there. While Penrose's work deepened our understanding of relativity, Hawking began to wonder what would happen if one dared to add quantum mechanics to the picture. For decades, relativity and quantum theory had stood apart like two grand but stubborn kings, each ruling its own domain. Relativity governed the vast, the stars, the galaxies, the cosmic dance. Quantum mechanics ruled the minute, the atoms, the electrons, the shimmering field of probabilities that gives matter its texture. Both were immensely successful, and yet together they clashed. Where relativity saw smooth curves, quantum mechanics saw restless fluctuations. Where one described certainty, the other spoke only of chances. Hawking's insight was to realize that black holes might be the perfect place where these two great languages of physics are forced to speak to one another. Near the event horizon, gravity is at its strongest, and yet, because of the immense curvature, quantum effects cannot be ignored. Here, at the edge of darkness, the laws of the very large and the very small must coexist. In that coexistence, Hawking sensed, there might be a doorway to the ultimate theory, a quantum theory of gravity. The beauty of this idea lies in its irony. For centuries, scientists had studied the heavens by looking outward, into the light of stars and galaxies. But Hawking's vision pointed inward, into the dark, where light itself could not escape. It suggested that the deepest truths of the universe might be found not in brightness, but in shadow. By the late 1960s and early 1970s, these ideas began to reshape astrophysics entirely. The term black hole, coined by John Wheeler, entered the language of science and poetry alike. What had once been a mathematical curiosity became something real, something astronomers began to search for in the sky. Theorists discovered that black holes could spin, that they could merge, and that their gravitational pull could ripple through the universe like waves across a vast cosmic ocean. These ripples, gravitational waves, would not be directly observed until many decades later, but the seeds were planted here, in this period of intellectual blooming. Meanwhile, Stephen Hawking, despite his physical decline from motor neuron disease, became the voice and face of this new era. His mind roamed freely where his body could not. From his wheelchair and his speech synthesizer, he spoke of horizons, singularities, and the unity of space and time. He asked questions that sounded almost like philosophy, but were grounded in rigorous science. Does the universe have boundaries? Can something truly vanish from existence? Are black holes eternal, or do they too fade? The collaboration between Penrose and Hawking marked a turning point in human understanding. They did not merely refine Einstein's theory, they expanded its reach. They turned black holes from forbidding curiosities into laboratories for the deepest questions about reality. It was as if physics itself had folded back on its origins, drawing light from the darkest places. The universe was no longer just a stage for stars to live and die. It was a dynamic, evolving, self-questioning system. Imagine, if you like, the universe as a grand piece of music. Einstein composed its melody. Penrose revealed the hidden harmonies. Hawking introduced the quantum rhythm that carried it forward. Together they transformed silence into song. As the 20th century entered its final decades, black holes stood at the crossroads of every major question in physics. They were not just destinations for matter, but meeting places for ideas, where relativity, quantum mechanics, thermodynamics, and philosophy all converged. What began as Einstein's discomfort had become humanity's fascination. And somewhere, deep in the quiet, between geometry and imagination, between the infinite and the microscopic, the universe was whispering a truth that even Einstein might have smiled to hear. Sometimes the path to understanding light leads first through darkness. When you imagine a black hole, you might think of a void so absolute that nothing, not even light, could ever escape. For centuries, that image defined how we understood these cosmic giants, perfect prisons of gravity, silent and eternal. But in the mid-1970s, Stephen Hawking discovered something that changed that picture forever. In one of the most surprising twists in modern physics, he showed that black holes are not perfectly black at all. They glow, faintly, quietly, yet undeniably. They emit light and particles into space. This gentle glow is what we now call Hawking radiation. It began as a thought experiment. Hawking was exploring what would happen if you combined Einstein's curved space-time with the strange world of quantum mechanics. In Einstein's universe, gravity bends light and warps the paths of everything that moves. In the quantum world, nothing ever stays still, not even the vacuum. What we call empty space is, in fact, alive with activity. Tiny pairs of particles flicker into existence and then disappear again, their brief lives too short for us to notice. This restless dance of creation and annihilation happens everywhere, all the time. Even in the quietest corners of the cosmos, the vacuum is humming softly with potential. Hawking asked what would happen to these quantum pairs near the edge of a black hole, at the event horizon, where gravity becomes almost unimaginably strong. There, the space-time fabric is so sharply curved that the normal rules of in and out, before and after, begin to blur. When a particle pair appears just at that edge, gravity can pull them apart before they have time to vanish. One particle falls inward, swallowed by the black hole. The other escapes, carried away into the universe as a faint whisper of radiation. To an observer far away, it looks as though the black hole itself is glowing, releasing a trickle of energy. To understand how faint this glow is, imagine trying to feel the warmth of a single candle on the other side of the moon. For a large black hole, the radiation is even weaker, so gentle that it would take longer than the age of the universe to notice any change. And yet, the implications are immense. The very idea that something could escape from a black hole challenges everything we once believed about them. It means that black holes are not eternal prisons. They have lifetimes, even if those lifetimes stretch beyond imagination. Over vast spans of time, this radiation slowly drains energy from the black hole. As it radiates, it shrinks, losing mass. The smaller it becomes, the hotter it gets, and the faster it glows, creating a kind of cosmic feedback loop. Eventually, after trillions upon trillions of years, the black hole would evaporate entirely, leaving nothing but its radiation behind. What began as the universe's most perfect absorber of energy ends, paradoxically, as an emitter. In the silence of the cosmos, even darkness itself fades. The beauty of Hawking's discovery lies in how it bridges opposites. It unites the smooth geometry of general relativity with the restless fluctuations of quantum theory. The black hole's horizon, once seen as a rigid boundary, becomes a place of delicate interaction, a seam where two great fabrics of physics are stitched together. It's as if the universe, through the black hole, is whispering that nothing is truly absolute, not even emptiness, not even darkness. To visualize this, imagine standing on a frozen lake at night. Beneath your feet, the ice feels solid, but tiny cracks form and vanish constantly, too fast to see. Now imagine that at the edge of the lake, where it meets a deep current, some of those cracks open just long enough for a droplet of water to escape into the air. Hawking radiation is like those fleeting droplets, moments when the boundary between stability and chaos allows a trace of energy to slip through. This radiation also carries something deeper, information about the black hole's nature. It behaves like heat, meaning black holes have a temperature. The larger the black hole, the colder it is. For a black hole the mass of our Sun, that temperature would be just a few billionths of a degree above absolute zero, colder than any natural place in the known universe. Yet that tiny temperature is enough to change our understanding of physics forever. It means that black holes obey the same laws of thermodynamics that govern stars, steam engines, and even a cup of tea cooling on a table. They are not exceptions to the universe's rules. They are part of them. This was a radical realization. Until Hawking's discovery, physicists believed that black holes were the ultimate sinks of energy and information, things that swallowed everything but gave nothing back. The idea that they could radiate like ordinary hot objects suggested something more profound. Perhaps they too were subject to entropy, the measure of disorder that guides the flow of time. In this sense, a black hole is not just a gravitational object, it is a thermodynamic one, a cosmic furnace that burns so slowly we can hardly see its flame. For Hawking, this finding was both exhilarating and haunting. It offered a glimpse of the long-sought unity between quantum theory and relativity, yet it also hinted at paradoxes still unresolved. If black holes emit radiation and eventually vanish, what happens to the information about everything that fell in? Does the universe lose those details forever, or are they somehow preserved in the faint light that escapes? These questions would lead to the famous information paradox, a problem that still echoes through physics today. But in that moment, Hawking had illuminated something extraordinary. Even at the edge of the unknowable, the universe continues to play by its own subtle rules. There is a quiet poetry in this revelation. The darkest objects in existence are not absolute voids, but gentle emitters of energy. They whisper to the cosmos, shedding light so faint it takes the mind of a mathematician to see it. The discovery of Hawking radiation turned black holes from symbols of destruction into symbols of balance, places where creation and annihilation, order and chaos, life and death all meet in perfect symmetry. It showed that even when matter vanishes, the conversation between the laws of physics never stops. If you listen closely, you can almost imagine it. The slow fading of a black hole across the eons, radiating warmth into the dark until only the echo of its existence remains. The cosmos does not waste. It recycles, transforms, and returns everything to its vast, quiet rhythm. And through the faint glow of Hawking radiation, it reminds us that nothing, not even the darkest night, can remain entirely without light. When Stephen Hawking first revealed that black holes glow, the scientific world marvelled. It was elegant, surprising, and strangely beautiful, a bridge between the vastness of relativity and the subtleties of quantum mechanics. But beauty often hides deeper puzzles, and this one held a riddle that would haunt physics for decades. It came to be known as the information paradox, and it began with a simple question. If a black hole can evaporate, what happens to everything that ever fell inside? In ordinary life, information feels permanent. You can burn a book to ashes, melt a statue into metal, or break a glass into dust. But in principle, the details of what once existed are never truly gone. If you had infinite patience, perfect instruments, and the ability to collect every atom, every photon released in the process, you could, at least in theory, reconstruct the original form. This is one of the cornerstones of quantum mechanics. Information is conserved. The universe keeps its memories, even when the form changes. But black holes seem to ignore that rule entirely. According to Hawking's calculations, the radiation that seeps from a black hole carries no trace of the things that fell in. The glow is perfectly thermal, featureless, uniform, like the faint warmth from a cooling ember. If a black hole eventually evaporates completely, its radiation spreads outward, leaving behind nothing that could tell you what once was there. The information about stars, planets, light, or even people appears to vanish from the universe forever. This was not just a minor inconvenience. It struck at the very heart of physics. The loss of information would mean that the fundamental laws governing reality were not truly predictable. It would mean that cause and effect could be broken, that the universe might forget its own past. For physicists, this was as unsettling as discovering that numbers sometimes stopped adding up. Nature, it seemed, was breaking its own promise of consistency. To visualize this paradox, imagine throwing a beautifully written book into a black hole. The story, the ink, the paper, all cross the event horizon and vanish. As the black hole glows faintly with Hawking radiation over countless ages, you wait for the faintest whisper of the story to come back. But the radiation carries no trace of letters or words. It's like trying to reconstruct a novel from the heat of the fire that burned it. The warmth tells you energy was released, but not how it was released. The meaning, the information, is gone. For decades, scientists wrestled with this problem. Some argued that information truly is lost, that black holes represent a kind of final erasure in nature. Others insisted that something must be missing from the theory, that a deeper quantum theory of gravity would somehow preserve the information in a hidden form. After all, the universe is careful with its ledgers. Energy cannot be destroyed. Why should information be any different? A few imaginative proposals emerged. Some suggested that information might be stored on the event horizon itself, encoded in an unimaginably subtle pattern, like ripples frozen into the surface of space-time. Others speculated that the information could somehow escape through quantum fluctuations, emerging slowly and unpredictably as the black hole shrinks. And then there were more exotic ideas. Perhaps the information slips into another universe, or perhaps it remains within the fabric of space-time in ways we do not yet understand. Each of these possibilities painted a different picture of reality, but none could yet be proven. What makes the paradox so haunting is that it lies at the intersection of everything we know and everything we don't. It's where Einstein's graceful geometry meets the jittering, uncertain sea of quantum fields. It's also deeply philosophical, because it forces us to ask what information really means. Is it a physical thing, a measurable property of matter, or is it something more abstract? The pattern, the order, the story that matter tells. If information can vanish, then the universe is not a storyteller, it is an editor that deletes without warning. But if information is somehow preserved, even in the faintest glow of Hawking radiation, then the universe is far more intricate than we can yet comprehend. Every particle, every photon, every vibration would carry a trace of the past, a cosmic memory encoded into existence itself. In recent years, new ideas have breathed life into the hope that information is not truly lost. The concept of holography, born from string theory, suggests that everything that happens inside a region of space may actually be described by information imprinted on its boundary. In this view, the universe is like a grand hologram, a three-dimensional world projected from two-dimensional data. Applied to black holes, this means that all the information about what falls in might be stored on the horizon's surface, just as a hologram encodes an entire image on a thin sheet of film. If this idea is right, then black holes are not destroyers of information, but keepers of it. Silent librarians holding the records of everything they consume, written not in ink but in the language of geometry. Still, no one has yet opened that library. The paradox remains unsolved, though every new theory brings us closer, and in the meantime, it serves as a gentle reminder of humility. The universe, vast and silent, continues to guard its secrets, showing us only what we are ready to understand. Perhaps one day, when our mathematics and imagination are both brave enough, the door will open and the story will unfold. There is a quiet beauty in the paradox itself. It reveals that even our most powerful ideas, relativity, quantum theory, thermodynamics, are not complete on their own. They are fragments of a larger truth, hints of a deeper order that unites them. The information paradox is not a failure of science, it is an invitation. It tells us that the universe still has mysteries worth losing sleep over, questions that reach beyond logic into wonder. And perhaps that is the real lesson, that knowledge and mystery are partners, not opposites. Just as a black hole radiates faint light from its darkness, understanding glows brightest when surrounded by the unknown. In that sense, the information paradox is not a riddle to be solved, but a reminder of what it means to explore, to look into the night sky and realize that every answer brings with it a deeper question, waiting quietly at the edge of gravity's pull. If you could somehow stand beside a black hole, hovering just beyond its invisible edge, and gaze at it with perfect clarity, you might expect to see complexity. After all, the star that gave birth to it could have been turbulent, chaotic, filled with storms of magnetic fire and swirling matter. You might imagine that this violence would leave some mark on the black hole, some signature or scar, a trace of its past. But nature, it seems, prefers simplicity. When a star collapses into a black hole, it does not preserve its details. It becomes a thing of pure geometry, stripped of personality, smooth and silent. This elegant simplicity is known as the no-hair theorem. The name itself comes from a bit of physicist humour. Hair, in this context, refers to complexity, messy, unique features that distinguish one object from another. A planet, for instance, has plenty of hair. It has mountains, oceans, and weather. A star has hair too, patterns of magnetic fields, spots, and layers of gas in motion. But a black hole, according to general relativity, has none of these adornments. It can be fully described by only three quantities: its mass, its spin, and its electric charge. That's all. Everything else, the composition of the star, its history, its chemical makeup, vanishes without a trace when the event horizon forms. The black hole forgets its past. In practice, this means that two black holes formed from completely different origins, one born from a massive blue star, another from the quiet collapse of a red giant, would look identical if they shared those three properties: the same shape, the same behaviour, the same gravitational field. From the outside, there would be no way to tell which was which. It's as though the universe takes the rich tapestry of a star's life and folds it neatly into a single smooth fabric. What was once intricate becomes perfectly plain. It's easy to imagine this as a loss, a kind of erasure. But there is also a quiet beauty in it. Nature at its extremes distills itself down to essence. The no-hair theorem is the mathematical expression of that purity. It says that gravity, when left alone to sculpt the cosmos, favours elegance over complication. The more extreme the conditions, the simpler the outcome. The black hole becomes the universe's most perfect minimalist. To visualise this, imagine a lake after a storm. While the wind rages, the surface churns with waves and foam, but once the storm passes, the water settles, smoothing into a flawless mirror. The black hole is that mirror. No matter how wild the collapse that formed it, no matter how many magnetic tempests or bursts of energy erupted during its birth, The result is a stillness so complete that even light cannot escape it. It reflects nothing outward, yet in its very simplicity it embodies the balance of the universe. This simplicity also carries a profound philosophical weight. If a black hole forgets the details of what created it, does the universe itself tend toward forgetting? Is simplicity the final truth behind all complexity? Many physicists see this as part of a larger pattern in nature. Across the cosmos, chaos often leads to order. Stars form from turbulent clouds, but settle into graceful spheres. Galaxies emerge from violent collisions yet rotate in elegant spirals. Even life, with all its diversity, arises from simple rules encoded in molecules. The no-hair theorem fits this pattern perfectly. It suggests that, beneath all the noise, the cosmos has a deep preference for harmony. But of course, this perfect simplicity raises questions. If black holes erase the fine details of their origins, how can information survive? This is where the no-hair theorem connects back to Hawking's radiation and the information paradox. The theorem applies within the framework of classical general relativity, where the event horizon is absolute and nothing can escape. But when quantum effects are included, those faint whispers of light that Hawking described, new possibilities emerge. Some physicists now suspect that the hair might not be entirely gone. Perhaps it is encoded subtly on the horizon itself, woven into the quantum structure of space-time like a pattern hidden in a fabric too fine to see. Stephen Hawking, Jacob Bekenstein, and others explored this idea by assigning black holes an entropy, a measure of how much information they could in principle contain. In this view, each tiny patch of the horizon holds a microscopic record of the matter that fell in. The black hole becomes not a blank void, but a cosmic archive, storing its history in the faintest quantum threads of space. The simplicity of the no-hair theorem, then, might be only an approximation, a smooth surface concealing unimaginable detail at the smaller scales. Even if those hidden patterns exist, they would be impossible to observe directly. To us, the black hole remains serene, featureless, its surface as calm as still water. The idea of hidden hair is not so much a contradiction as an evolution, a way of saying that simplicity and complexity can coexist. From afar, the black hole looks utterly smooth, but up close, at the quantum level, its surface may shimmer with subtle information, like a piece of silk that appears uniform until you hold it to the light, revealing an intricate weave beneath. This balance between appearance and reality is one of the most poetic truths of modern physics. The no-hair theorem teaches us that the universe wears its complexity lightly. It reminds us that perfection can be quiet, that simplicity can be powerful, and that sometimes what looks like emptiness is simply information resting in disguise. It also speaks in a way to human experience. We too are shaped by layers of detail, memories, choices, the turbulence of living. And yet beneath those layers lies something simple and universal, the shared geometry of being, the pattern that connects all things. A black hole, stripped to its essence, mirrors that same truth. It is pure curvature, pure existence, without ornament or story. A reminder that the universe at its most extreme is both strange and serene. If you could see a black hole not with your eyes but with your imagination, you might not see darkness at all. You might see balance, an unbroken symmetry between what was and what remains. The calm after collapse. The silence after the storm. The perfect simplicity that lies beyond chaos. Far from the vast centres of galaxies scattered across the quiet reaches of space, lie the most common kind of black holes, those born from the deaths of ordinary stars. They are called stellar mass black holes, and though they are small compared to their supermassive cousins, they carry the same elegance, the same mystery, and the same quiet power. Each one is a tombstone carved into space-time, marking where a star once burned with light, now collapsed into silence. To understand how such a black hole forms, we must return once more to the life of a star. A star, even one much larger than our Sun, spends most of its life in balance. Deep inside, nuclear fusion converts hydrogen into helium, releasing energy that pushes outward against the inward pull of gravity. It is delicate equilibrium, a cosmic truce that can last millions or even billions of years. But nothing lasts forever. When the nuclear fuel in a massive star runs out, gravity reclaims its strength. The outward pressure weakens, and the star begins to fall inward upon itself. At first, the collapse is slowed by the star's internal forces. Its electrons and neutrons resist being squeezed too tightly. But if the star is heavy enough, roughly more than 3 times the mass of our Sun, no known force can stop the fall. The core shrinks, heating as it does, until the atoms themselves are crushed. The outer layers rebound in a cataclysmic explosion, a supernova that can outshine an entire galaxy for a brief moment. What remains at the centre is something astonishingly compact, a sphere of gravity so intense that not even light can escape. The star's identity is gone, replaced by the geometry of its collapse. A black hole is born. These stellar mass black holes are typically just a few tens of kilometres wide, smaller than a city, yet containing more mass than several suns combined. To imagine this density, think of compressing the Earth into a sphere no larger than a marble. In that form, its gravity would be so strong that even light would curve back to it. For a black hole 10 times the mass of the Sun, this event, horizon, the invisible boundary from which nothing can return, would span barely 60 kilometres. Inside that boundary, space itself is drawn inward faster than anything can move outward. It is not a solid object. It is a region of space-time shaped by gravity's own logic. Yet, despite their power, stellar black holes are usually quiet. Once formed, they drift unseen through space, leaving no visible trace unless they interact with something nearby. If a black hole travels alone, there is nothing to mark its presence. No light, no reflection, no sound. It passes through the galaxy like a ghost, influencing only through its gravity. A star that happens to orbit such a black hole will wobble, its path betraying the presence of an invisible partner. From Earth, astronomers detect these subtle wobbles and infer the hidden mass that must be pulling them. The unseen object is not speculation. It is measurable, predictable, real. Sometimes, though, black holes reveal themselves more dramatically. When a black hole has a companion star, gravity begins a slow and relentless exchange. Gas from the star is drawn outward, spiraling toward the black hole in a glowing whirlpool called an accretion disk. As the gas falls inward, it heats to extraordinary temperatures, shining in X-rays and ultraviolet light. From a distance, we see this as a brilliant beacon, the black hole's quiet feeding made visible. Yet even then, what shines is not the black hole itself, but the matter it consumes, heated to incandescence as it crosses the point of no return. The physics of this accretion is astonishingly efficient. A typical nuclear reaction, like the fusion that powers the Sun, converts less than 1% of matter into energy. But matter falling into a black hole can release up to 40% of its mass as radiant energy before vanishing. It is one of the most powerful energy processes in the universe, rivaled only by the birth of stars themselves. From this perspective, black holes are not merely destroyers, they are engines of creation, returning energy to the cosmos in bursts of light that shape galaxies and stir interstellar gas into new forms. And yet, for all their power, there is something almost peaceful about them. The violence of collapse has passed. What remains is stable, enduring, and silent. Left alone, a stellar black hole can persist for trillions upon trillions of years, gradually evaporating through Hawking radiation only in the unimaginable future. They are monuments to impermanence, lasting longer than the stars that birthed them, longer than galaxies themselves may exist. The experience of falling toward one, if it were possible to survive long enough to notice, would be both mesmerizing and fatal. The closer you come, the stronger gravity's pull becomes, until the difference between your feet and your head stretches your body like taffy. Physicists call this tidal stretching, though popular imagination prefers the term spaghettification. Near smaller black holes, this stretching would tear atoms apart long before you reach the horizon. But near supermassive black holes, whose horizons are vast and gentle, you could cross the boundary without feeling it. Inside, however, the path always leads inward, to the place where time and space themselves fold into the singularity. Astronomers have found dozens of stellar mass black holes in our galaxy, and suspect there are millions more, hidden among the stars. They form quietly at the end of stellar lifetimes, one by one, like candle flames going out in the night. In binary systems, where two stars orbit each other, black holes can even merge, sending ripples of gravitational waves across the universe, faint vibrations in space-time that we can now detect. These waves are like echoes of their union, soft and fleeting, yet carrying the signature of their masses and spins. Each detection tells a story, two invisible objects dancing together, colliding and becoming one. It's humbling to realize that these small, dark remnants are everywhere. For every visible star that shines, there may be several others that have already collapsed. They drift through the Milky Way like silent seeds, shaping the orbits of stars, bending the paths of light, influencing galaxies in ways we are only beginning to see. And though they are the remnants of death, they play a role in the ongoing life of the cosmos, recycling matter, stirring gas, creating the conditions for new stars to form. When you look up at the night sky and see thousands of points of light, remember that for every star still shining, there is another that has gone dark. Its story has not ended, it has simply changed shape. Somewhere, perhaps within a few thousand light years, a stellar mass black hole drifts unseen, patient and eternal, the memory of a once brilliant star folded into the quiet geometry of space. In the end, that may be the most poetic truth about these small black holes. They remind us that endings are never truly endings. The energy that once burned as light continues to echo through the universe in subtler forms. Even in darkness, the story of creation goes on. At the quiet heart of nearly every galaxy in the universe, including our own, there lies a presence both ancient and immense, a supermassive black hole. These giants are nothing like the stellar mass black holes born from the collapse of single stars. They are far older, far larger, and far more mysterious. While a stellar black hole might weigh a few suns, a supermassive black hole can contain the mass of millions or even billions of suns, all compressed into a region smaller than our solar system. They sit in silence, steady and patient, shaping the galaxies that spin around them like dancers circling a hidden conductor. The black hole at the centre of our Milky Way is called Sagittarius A star. It rests about 26,000 light-years away, cloaked behind veils of interstellar dust. Though it is invisible to our eyes, astronomers can trace its presence through the movement of nearby stars. These stars orbit a seemingly empty point in space, racing around it at speed so great that only an object 4 million times more massive than our Sun could hold them in place. That invisible point, small, dense, and perfectly dark, is our galaxy's heart. The story of how these titans formed remains one of astronomy's great mysteries. Some scientists believe they were born in the earliest days of the universe, when the first stars burned and died, leaving behind black holes that grew by consuming gas and merging with others. Others think they might have formed directly from enormous clouds of matter collapsing before stars could even ignite. However they came to be, once a supermassive black hole exists, it becomes the gravitational anchor of everything around it. Its influence extends far beyond its horizon, shaping the motion of billions of stars and sculpting the delicate spiral arms of galaxies. Despite their reputation for consuming, supermassive black holes are, in truth, architects of cosmic balance. When matter drifts too close, clouds of gas, drifting dust, or entire stars, the black hole's gravity pulls it inward, forming a swirling disk that glows hotter than anything else in the universe. This is called an accretion disk, and its edges can reach temperatures of millions of degrees. The radiation from this disk can outshine every star in the galaxy combined, creating what astronomers call a quasar, a beacon so luminous that it can be seen across billions of light years. Through these rare, energetic moments, black holes shape the growth and behaviour of their host galaxies, controlling when and where new stars are born. It is almost paradoxical. The most destructive objects in the cosmos are also its great nurturers. Without the gravitational influence of these colossal centres, galaxies might never have formed the graceful structures we see today. The slow spin of a galaxy, its luminous arms and sweeping symmetry, all trace back to the stabilising hand of the dark mass at its centre. Even the distribution of matter across the universe bears the fingerprint of these giants. In their stillness, they maintain the rhythm of creation. Imagine for a moment standing far above a galaxy, looking down upon it as it turns. The spiral arms stretch outward like the arms of a celestial whirlpool, each star moving in harmony, each orbit guided by the unseen weight at the core. That invisible presence does not shine or shout. It simply is, exerting its influence quietly, its gravity the melody beneath the song of the stars. Astronomers have found supermassive black holes not only in large galaxies like the Milky Way, but even in smaller, faint ones, dwarf galaxies barely bright enough to notice. This suggests that black holes and galaxies are companions from the beginning, growing together like twin trees with their roots entwined. When galaxies merge, their central black holes spiral inward toward one another, locked in an invisible waltz that can last millions of years before they finally unite. When they do, the collision sends ripples through space-time, gravitational waves that travel across the universe, gentle tremors in the very geometry of existence. Each wave carries a story of two galaxies becoming one, their histories joined forever. Our own galaxy's central black hole is, by cosmic standards, rather calm. It occasionally feeds on stray gas or dust, producing soft flares of X-rays, but for the most part, it rests. In other galaxies, the story is more dramatic. Some supermassive black holes consume so voraciously that they drive colossal jets of plasma into space, streams of charged particles that shoot out at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, shaping the surrounding gas and influencing how new stars form. And yet, even in their violence, these phenomena follow the same quiet logic. Energy transforms, matter moves, and the universe remains in balance. What makes supermassive black holes so captivating is not just their size, but their duality. They are both creators and destroyers, both stable and dynamic. They embody the universe's tendency to recycle, to use even gravity's most extreme expression as a tool for order. The same equations that predict collapse also predict renewal. Out of falling matter comes light. Out of stillness comes structure. It is as though the universe, through these vast engines, demonstrates that destruction and creation are simply two directions of the same flow. When astronomers first realized that these black holes existed, the discovery seemed almost mythic. To think that every galaxy, every great island of stars, harbours an invisible centre of immense gravity was both humbling and exhilarating. It gave the cosmos a new kind of symmetry, as if each galaxy were a living organism with a beating heart of darkness. And like all living things, these hearts can be both peaceful and fierce, sometimes resting quietly, sometimes roaring with energy as they feed. Even here, though, the paradox remains. From the outside, a supermassive black hole is pure simplicity. Its event horizon is smooth and silent, revealing nothing of the chaos within. Yet on a galactic scale, its influence is intricate, shaping entire systems and giving form to the luminous architecture of space. It is a reminder that simplicity does not mean insignificance. Sometimes the calmest things hold the most power. When you gaze at the night sky and see the faint river of the Milky Way stretching above you, you are, in a sense, looking toward that hidden centre. Sagittarius A star lies behind the dense clusters of stars and dust in the constellation of the Archer, quietly binding the galaxy together. Its gravity keeps us in orbit, steady and secure. We owe our position in the cosmos, and perhaps even our existence, to a presence that does not shine. The stars we see are merely the outer expression of its silent design. In the end, supermassive black holes remind us of something simple but profound, that even the greatest forces in the universe act with patience. They shape galaxies not in moments, but over billions of years. They are proof that the cosmos evolves through balance, that light and darkness are not opposites but partners in creation. At the heart of every shining galaxy lies a quiet truth. The most powerful forces in nature need not be loud. They simply hold everything together. For most of human history, black holes were invisible not only to the eye, but to the imagination. They were mathematical ghosts, beautiful on paper but impossible to see. Even after their existence became accepted, they remained elusive, cloaked behind horizons from which no light could escape. But the universe, in its patience, always leaves traces of what it hides. Over the past century, astronomers have learned to find black holes not by seeing them directly, but by listening to the faint echoes they leave behind, the trembling of nearby stars, the shimmer of hot gas, the ripples of space-time itself. In this way, we have learned to detect the invisible. The first clues came from the behaviour of stars. Some stars, astronomers noticed, appeared to be orbiting something unseen, an invisible companion pulling them with immense gravity. The most famous early example was Cygnus X1, discovered in the 1960s. It was a binary system, a visible star and an invisible partner emitting powerful X-rays. The radiation came not from the hidden object itself, but from a swirling disk of gas drawn off the companion star, heated to extraordinary temperatures as it spiraled inward. The patterns of those X-rays told astronomers that the invisible object had a mass far too great to be a neutron star. It could only be a black hole. For the first time, the idea leapt from theory into observation. Since then, the methods have grown more subtle, like learning to see by touch and sound rather than by light. Astronomers watch for stars that wobble, their orbits betraying the tug of an unseen partner. They measure the flickering of X-rays, the spectrum of energy, and the timing of the flares that escape before matter crosses the event horizon. Each observation adds a stroke to the unseen picture. When combined, they form a portrait of something that cannot be directly painted. Another method, both elegant and haunting, is gravitational lensing. According to Einstein's general relativity, massive objects bend the paths of light passing near them, curving space itself. When a black hole drifts in front of a distant star or galaxy, it can act as a cosmic lens, magnifying and distorting the background light. To us, the distant star seems to brighten and fade, as though a ghost had passed before it. These subtle shifts allow astronomers to measure the black hole's mass and position, even though the black hole itself remains unseen. The universe, once again, reveals itself through shadows. But perhaps the most profound confirmation of black holes came in 2015, when the LIGO observatories recorded a signal that had travelled for more than 1 billion years. 2 black holes, each dozens of times heavier than our Sun, had spiraled together and merged. The collision sent out ripples in space-time, gravitational waves, that spread across the cosmos like ripples on a pond. When they reached Earth, they stretched and compressed everything by less than the width of an atom, yet our instruments were sensitive enough to feel that faint trembling. In that moment, we heard the universe speak in a new language. The sound of two black holes merging, rising, swelling, fading, was not just data. It was a kind of cosmic music. We had listened to gravity itself. These gravitational waves confirmed predictions made a century earlier. They also opened a new era of astronomy, one that does not rely on light at all. For the first time, we could study the universe through its vibrations, hearing its deep tones instead of seeing its brilliance. Each detection since then has been like listening to another verse in a song that has been playing since time began. Some of these waves come from black holes merging, others from neutron stars colliding. Each tells a story about matter, energy, and the unseen architecture of space-time. Then, in 2019, the invisible finally took shape. The Event Horizon Telescope, a global network of radio observatories acting in unison, captured the first image of a black hole's shadow. The object was a supermassive black hole at the centre of the galaxy M87, 55 million light-years away. The image was not a direct photograph of the black hole itself, nothing can escape to be photographed, but of the glowing ring of gas swirling just outside its horizon. Against that fiery halo, the black centre stood out, a perfect silent circle, the silhouette of space-time collapsing inward. Humanity had for the first time seen the outline of the unseeable. The precision of that observation was astonishing. To create it, scientists linked telescopes around the world, from the deserts of Chile to the mountains of Hawaii and the frozen plains of Antarctica. Together, they formed a virtual telescope the size of Earth itself. When the data was combined, pixel by pixel, the result was both scientific and deeply emotional. A blurred ring of light encircling darkness. It was a glimpse into the most private part of the universe, a confirmation that our equations had been right all along. The photograph was proof that even what hides can leave a mark. That reality, however strange, always leaves evidence of itself. In the years since, the Event Horizon Telescope has turned its gaze toward other black holes, including Sagittarius A star at the centre of our own galaxy. There, too, behind the thick clouds of cosmic dust lies a similar ring of glowing gas, smaller and more delicate but no less profound. It turns slowly, its light bending around the black hole's gravity, giving us not only a picture but a sense of motion, like watching the slow breathing of the cosmos itself. All of these discoveries remind us that seeing is only one way of knowing. The universe speaks in many tongues: light, sound, gravity, and time. Black holes, once thought to be the ultimate silences, have become teachers of connection. Through them, we have learned that even when something hides its light, it can still shape the world around it. A star's orbit, a flicker of X-rays, a ripple in space-time, each is a message from the dark. And there is something deeply human about this act of detection. We are creatures of curiosity, tracing faint clues to understand what lies beyond sight. To find a black hole is to prove that knowledge can reach into the invisible, that patient observation and imagination together can reveal the shape of mystery itself. Every image, every wave, every flicker of light pulled from the edge of a black hole is a triumph of both science and wonder. When you look at those glowing rings of gas or hear the distant hum of merging black holes recorded by instruments on Earth, you are hearing the echo of something timeless. You are listening to gravity itself speaking across eons to light bent by its own longing to escape. The cosmos, it seems, does not hide to taunt us. It hides to invite us. It wants to be seen, but only by those who are willing to look with patience, to listen with care. So as we learn to detect the invisible, we also learn something about ourselves. That curiosity is our own form of gravity, pulling us ever closer to understanding. The universe may be vast, but it is not indifferent. Through black holes, it reaches back, whispering in the faintest waves and glows, reminding us that even in darkness, connection endures. As our understanding of black holes deepened, something remarkable began to happen. What started as a story about gravity and collapse transformed into something larger, a meeting place for the deepest mysteries in all of science. In their silence, black holes whisper about the unity of everything. They are where the vast and the tiny, the cosmic and the quantum meet face to face, and it is there, at the edge of the impossible, that we glimpse the outlines of a new understanding, a theory that might finally bring together the two great languages of nature, relativity and quantum mechanics. Einstein's general relativity describes the grand architecture of the cosmos. It tells us how space and time curve, how stars and galaxies move, how gravity shapes everything from the orbits of planets to the expansion of the universe itself. It is smooth, continuous, elegant, like a flowing fabric that bends and ripples in response to matter and energy. Quantum mechanics, on the other hand, rules the small, the world of atoms, particles, and the flickering energy of the vacuum. It is a place of uncertainty and probability, where events happen not with certainty but with chance, and where reality seems to shimmer between being and possibility. Each theory works perfectly in its own domain, but at the heart of a black hole they collide. Relativity predicts smooth geometry. Quantum mechanics predicts restless motion. Near the singularity, where gravity becomes infinitely strong and distances vanish, these two descriptions can no longer agree. Relativity says the curvature becomes infinite. Quantum theory says infinity cannot exist. Somewhere between the two, a deeper truth must reside, a truth that neither theory alone can tell. That deeper truth is what physicists call quantum gravity, a theory that would merge the continuous fabric of space-time with the granular, probabilistic dance of the quantum world. And black holes, by their very nature, are the perfect laboratories for this search. They compress the universe's most extreme conditions, enormous mass, tiny size, immense gravity, into one small silent point. If we can understand how physics behaves there, we might unlock the hidden rules that govern all of reality. In this pursuit, black holes act as teachers. They challenge every assumption we make about space, time, and information. They ask questions so simple they sound poetic. What happens when space ends? Can time have an edge? Does the universe remember everything it has ever done? In trying to answer them, we are forced to reconsider what reality even means. One of the most promising clues comes from the study of holography, a concept we touched upon earlier. Imagine that every event happening inside a black hole, or even inside the universe itself, could be described by information stored on a boundary, a kind of cosmic screen. This idea, known as the holographic principle, suggests that our three-dimensional world might be a projection from data encoded on a two-dimensional surface. It sounds fantastical, but it has a firm mathematical foundation. It may be that space-time itself emerges from quantum information, woven together like a tapestry of probabilities. If this is true, then black holes are not just holes in space. They are keyholes through which we can glimpse how reality is constructed. Another clue comes from attempts to apply quantum theory directly to the curvature of space. Some approaches, like loop quantum gravity, propose that space-time is made not of a continuous fabric, but of tiny, discrete loops, like a cosmic mesh so fine we can never touch its individual threads. Others, such as string theory, imagine that all particles and forces, including gravity, arise from the vibrations of infinitesimal strings of energy. In both views, the singularity inside a black hole might not be a true point of infinite density, but rather a place where our familiar notion of space breaks down, replaced by something smaller, stranger, and smoother. Infinity, in this sense, might be an illusion. just the shadow of our incomplete understanding. While these theories differ, they share something profound. They all see black holes as the ultimate test. Because if a theory of quantum gravity cannot explain what happens inside a black hole, it cannot explain the universe. And so, with each new observation, each gravitational wave, each image of an event horizon, we take one step closer to answering Einstein's final question. How does gravity fit into the quantum world? What makes this search so moving is that it's not merely technical, it's philosophical. To seek quantum gravity is to seek the harmony of opposites, order and uncertainty, smoothness and granularity, determinism and probability. It is a search for unity in a universe that appears divided, and black holes, silent and patient, sit at that intersection like cosmic sages, waiting for us to listen closely enough to hear what they've been saying all along. In their presence, our understanding of time itself begins to change. If space-time is quantized, made of tiny discrete units, then perhaps time too is not continuous but comes in pulses, like the beats of a hidden rhythm. Perhaps what we perceive as the flow of time is the unfolding of quantum information, one note at a time, played across the vast instrument of the universe. The black hole then becomes not an endpoint but a measure of that music, a tempo by which we might understand the song of creation. Even now, as our technology grows sharper and our theories more intricate, black holes remain just beyond full comprehension. They are like distant lanterns half veiled in fog, illuminating both what we know and what we have yet to discover. They remind us that science at its best is not about final answers, but about deeper questions, questions that stretch our minds and humble our certainties. And perhaps that humility is part of their lesson. Einstein once doubted that black holes could exist. To him, they were mathematical curiosities, outcomes too extreme for nature to allow. Yet today, we see them as cornerstones of the universe, as quiet gateways through which reality itself may be trying to reveal its structure. It is a gentle reminder that even our greatest theories are not destinations but paths. The horizon is not an end, it is an invitation. So as we look back across the journey, from the first ideas of dark stars in the 18th century, through Einstein's doubts, through Hawking's revelations and the glow of Hawking radiation, to the faint hum of gravitational waves and the first images of a black hole's shadow, we see a story not of despair, but of connection. Every discovery, every paradox, every challenge has brought us closer to the same truth, that the universe is a single, continuous act of becoming, written in both light and darkness. And if you listen closely in that darkness, you might almost hear the universe breathing, slow, steady, patient. The same breath that once carried starlight now hums quietly around black holes, where gravity and quantum theory meet. These sleeping giants are not the end of understanding, they are its beginning. They sit in the night, silent but radiant in meaning, teaching us that even in the deepest shadow the universe is still awake.